Good evening, my dear student friends. Today we are going to discuss about time domain specifications or transient response specifications. Okay, so last class when discussed on the time domain response of the second order system, right? So what is the step response of second order underdamped system? Step response, right? So step response of second order underdamped system. Underdamped system. Okay. So what is the step response? C of t equal to 1 minus e to the power minus zeta omega n t divided by square root of 1 minus zeta square of sine omega td plus phi. Am I right? So this is the step response of the second order system. So what is the step response of the second order system? So 1 minus e power minus zeta omega n t divided by square root of 1 minus zeta square sine of omega d t phi, where omega d is equal to omega n square root of 1 minus zeta square. So damped frequency of oscillations. Whereas phi is phi equal to tan inverse of square root of 1 minus zeta square divided by zeta. Right? So from this response we can able to find different time domain specifications. So if you put C of t, when C of t at t equal to 0, initial response. So what is the initial response value? C of t equal to 0. So then C of t when at t equal to infinity. So at infinity, C of t equal to 1. Right? So 1. Say the step response of the second order underdamped system will be like this. So this is when t equal to 0. This is the value when t equal to infinity. So here t equal to infinity. So from this response, second order underdamped response, we can able to identify the different parameters. First one is delay time. So this is a delay time. Delay time. This is rise time. PR equal to rise time. Rise time. TP equal to peak time. Peak time. Right? TS equal to, there are two settling time for two tolerance. So settling time for 2% tolerance. Okay. So this is settling time for 2% tolerance. And this is 2% tolerance. This is for 5% tolerance. So settling time. Settling time for two values, two tolerances, one for 2% tolerance, other one for 5% tolerance. So this is a maximum overshoot, first peak. Okay, so MP is nothing but maximum overshoot. Maximum overshoot. So this is the steady state value 1. So steady state value is 1. Clear? So these are all the various time domain specifications. Let us derive these values, these time domain specifications. Okay. So first one is what is delay time. So delay time is, first one is delay time. What is delay time? TD. T suffix D. What is delay time? Okay, it is the time taken by the response from 0 to 50%. So this is steady state. This is 50%. So the time taken to reach from 0 to 0.5, right? 50% of the steady state value, final or steady state value. Okay, so that is C of T. What is the value? C of T at T equal to TD equal to 0.5, 50%, 0.5. Steady state value is 1. So what is TD? TD equal to, it is given by TD equal to 1 plus 0.7 zeta divided by omega n. This is the formula for delay time. This is the time taken by the system, control system, to reach from 0 to 50% of the steady state value. So this is delay time. Okay. Next, rise time. Okay. Next is rise time. What is rise time? Rise time. Okay. TR. So what is rise time? It is time taken by the system to reach 0 to 100%. To reach, time taken by the system to reach from 0 to 100% of the steady state value. Okay. Generally, in general, it is 10% to 90% for 90% for overdamped system. This is for time taken by the system. This is for overdamped system. Okay, and critically damped system, for critically damped system, 5% to 95%. 95%. So time taken by the system from 5% to 90%. This is for critically damped system. Critically damped. When zeta equal to 1. The zeta is greater than 1. Okay. Zeta is greater than 1. Clear? So time taken by the system to reach 0 to 100%. This is for under dam. Under dam. Okay. So how to find this rise time? So we can derive from the C of T. So C of T equal to 1 minus e to the power minus zeta omega n t divided by square root of 1 minus zeta square sine omega d t plus 5. Am I right? So C of t, what is the rise time from 0 to 1? Okay, so we can replace C of t equal to 1 and put wherever t is there equal to tr. Okay, substitute t equal to tr and also the value is 1. So substitute the values here. So what happened? So C of t 1 equal to 1 minus e to the power minus zeta omega n t or divided by square root of 1 minus zeta square sine omega d tr plus 5. So 1 cancel e to the power. Okay. So this is equal to 0, right? This is equal to 0. This is equal to 0. So sine of so there are two terms. One is this term, other one is this term. So this term may not be equal to 0. This is equal to sine can be 0, but this e to the power zeta omega and t term may not be 0, right? So we can equate this sine omega dt, sine omega dt plus phi equal to 0. Okay, so this is possible, but this is not possible. So what is TR nice time? So this, what is sine 0? This is n phi. Okay, sine of n phi, sine phi. Okay, sine n phi. So this is equal to 0. Instead of 0, sine n phi, sine n phi. So sine cancel, omega d TR plus phi equal to n phi. So actually this is the rise time from 0 to 100% of the steady state value during first attempt. So we can take the n value equal to 1. So n value equal to 0, 1, 2, 3, etc. Okay, so this n value we can put for first attempt, n value equal to 1. So from this, what is TR? TR equal to pi minus phi divided by omega d. So this is the expression for rise time. Expression for rise time. So pi minus phi, that is phi. Phi should be taken in radian. So tan inverse of square root of 1 minus zeta square divided by zeta. So this is the expression for rise time. Next is peak time. Okay, peak time. Peak time. So TP. So how to find peak time? So peak time is again we have to consider the step response equation. So to find the maximum and minimum, we should differentiate. Okay, to find it. So first peak. Okay, so we have to differentiate the response equation. dc of t by dt equal to 0. Then replace wherever t is there, replace TP. Okay, replace TP. So again we consider C of t. If we differentiate this expression, so what do you get? To get the peak or maximum value or minimum value, we should differentiate the expression with respect to t, right? So what do you get? So dc of t divided by dt equal to 1, for differential of 1 is 0 minus e to the power, say what we can take 1 by square root of 1 minus zeta square. So there are two terms. We can differentiate UV method. So what do you get? E to the power minus zeta omega nt. Okay, put TP, right? TP into minus zeta omega n of this is the differential of u, right? Then we simply put the sign next term, sine omega d Tp plus phi, plus keep this term as a constant u zeta omega n Tp, okay, into differential of this term. So cos omega d Tp plus phi into omega d. Am I right? So you take the common parameters from this. So what do you get? E to the power minus zeta omega n T P Then we can remove zeta omega n also, zeta omega n from the both term, or say you can remove only omega n. Okay, omega n is a common term. So remaining divided by, this is minus, divided by square root of 1 minus zeta square. Remaining term is minus zeta sine omega d tp plus 5 plus here in this term what we removed omega n outside, so remaining is square root of 1 minus zeta square into cos omega d tp plus 5. Clear? So this is equal to 0. So this term equal to 0. Okay. So this term may not be equal to 0, but this term will be 0. Here you can write instead of zeta, we can substitute as a from the pole zero diagram. So what is zeta? Zeta is the cos term, right? So this side is 1 minus zeta square. Okay, so this is 1. So zeta cos phi. So this can be taken as cos phi. Instead of this, sin phi. Okay, so cos sin phi into sin theta, sin A into cos B, cos A into sin B, right? Minus cos A into sin B. So what do you get? So this is say cos A. You can take phi as A, phi as A. This as B. Okay. So this can be written as sine of omega d tp plus 5 minus 5 equal to 0. 5 cancel. So sine of omega d tp equal to sine n phi. Sine n phi. So where n equal to, you can take it, n equal to 0, 1, 2, 3, etc. So the n equal to 1 for first peak. Okay, first peak. So what do you get? We can get omega d tp equal to 5. Okay, so what is tp? tp equal to pi by omega d. Omega d. Pi by omega. Understand? So this is one method. We can also do from this step. From this step, we can also do. You see, this is zeta omega n. We can keep inside. So zeta omega n sine of this. Similarly, here omega d into cos phi, right? So as usual, we can from this step we can also get. So this is the peak time expression. Understand? So the time period, okay, the time period of damped oscillations is equal to the twice of the peak time. That is 2 TP. Clear? So TP equal to this seconds. Unit is important, seconds. Okay, so you see the first peak overshoot, second overshoot, etc. So this is the steady state value. Okay, so this is first. This is first overshoot. Okay, so this is one. This is a settling tag, settling. So first overshoot. This is first overshoot. So this is equal to pi by omega d. First undershoot. So this is first undershoot. So this is 2 pi by omega d. Second overshoot. This is first undershoot. This is second overshoot. Okay, this is second undershoot. So this value equal to 3 pi by omega d. 3 pi by omega d. This is 4 pi by omega d. 4 pi by omega d. Understand? So this is peak time. So the time period of damped oscillations equal to the twice of their peak time, 2 times peak time. So next is maximum overshoot. Maximum overshoot or peak overshoot. Maximum or peak overshoot. That is MP. So how to get MP? So MP is the so this is MP. So what is this MP value? So this is C of TP. This is C of TP. TP. So what is TP? TP equal to pi by omega t. First peak overshoot. So the maximum overshoot is the difference between these two. So this is C of steady state. C of t equal to infinity. So what is MP? Maximum overshoot equal to percentage overshoot equal to C of TP minus C of infinity divided by C of infinity. Okay, C of infinity into 100%. Into 100%. So this is the percentage overshoot. Clear? So what we have to do in C of t expression, substitute t equal to TP. Okay, so replace t equal to TP. What is TP? Substitute wherever TP is there, t is there, pi by omega t. So 1 minus e to the power minus zeta omega n TP divided by square root of 1 minus zeta square sine of omega d TP plus 5. Here, so substitute the values. C of TP equal to (1 minus e to the power minus zeta omega n). Instead of TP, it's up pi by omega d, that is omega n square root of 1 minus zeta square divided by square root of 1 minus zeta square into sine omega d into Tp value is pi by omega d plus pi. Omega d cancel. Sine of pi plus pi. Okay. Sine of pi plus pi is, what is sine of pi plus pi? My dear, tell me, what is sine of pi plus pi? Okay. Pi, no change. Okay. But here minus, instead of minus, we'll be getting plus. Right. So this becomes sine phi. So 1 plus sine of, this is sine of pi plus pi. So no change, but sine will become a negative. Pi plus pi, third quadrant. So minus sine pi. So here become plus. So e to the power. So this will be omega n cancel. E to the power minus, yeah, pi zeta pi divided by square root of 1 minus zeta square. Everything exponential to the power into divided by square root of 1 minus zeta square sine pi. So what we get here? So this, instead of this, we can replace sine phi. So sine phi cancel. So C of Tp equal to 1 plus square root of 1 minus zeta square. So C of Tp equal to 1 plus e to the power minus zeta pi divided by square root of 1 minus zeta square. Okay. So now what is MP percentage MP? Percentage overshoot equal to C of Tp minus, so 1 plus e to the power minus zeta pi divided by square root of 1 minus zeta square. Everything is exponential to that, minus C of 1 divided by 1 into 100%. So 1 cancel. So maximum percentage overshoot MP equal to e to the power minus zeta pi divided by square root of 1 minus zeta square. So this is the expression for maximum overshoot. Okay, maximum overshoot into 100 we put percentage maximum overshoot into 100. So this is called. So if the input is doubled, the important point is, if the input is doubled, okay, then the steady state and the peak values doubled, then the steady state and maximum peak values, maximum or peak values doubled. Okay, therefore MP also doubles, but the percentage peak overshoot, it remains constant. remains constant, right? Remains constant. Then settling time. Actually, settling time I explained for two ranges. So one for two tolerances. Actually, in this diagram, there are two fellows in the expression. This is the characteristic. This is the equation of this curve. C of t equal to 1 minus e to the power minus zeta omega n t divided by square root of 1 minus zeta square sine omega dt plus 5. So out of these two fellows, so this is one fellow, this fellow e to the power, this is the exponential fellow, this is sine fellow. So sine. So this fellow always oscillate, okay, oscillate. So sinusoidal, okay, oscillating. Whereas this fellow, this exponential fellow tries to pull down, tries to settle the system. So among these two, this fellow e to the power minus zeta omega n t, okay, this fellow is responsible for settling. So we can use that expression here to find settling time, okay. So settling time. Settling time. TS. So it is the time taken by the response to reach either plus or minus 2% or plus or minus 5% tolerances. Tolerance band. Okay, tolerance band. So at t equal to ts, the oscillations is almost nullified. Okay, when t equal to ts, oscillations almost, okay, oscillations almost nullified, almost zero. Okay, hence in the response, the exponential term is only considered. Okay, that is responsible for tolerances. So TS for 5% tolerance, first we find. So you can equate e to the power minus zeta omega n tr equal to plus or minus 5%. That is 0.05. So if you take log on both sides, okay, take log on, apply log on both sides. So minus zeta omega n tr equal to log of 0.05 is almost 3. Okay, so nearer to 3. So tr, so this is minus 3. So tr for 5% tolerance is 3 divided by zeta omega n. Zeta omega n. Okay. So 1 by tau equal to time constant of the second order system is zeta omega n. So for 5% tolerance, tr equal to 3 times tau. As in the case of first order system, 3 times tau. Similarly, when ts for 2% tolerance, same equation. So e to the power minus zeta omega n tr equal to plus or minus 2% equal to 0.02. Apply log on both sides. You will be getting minus zeta omega n tr equal to natural log of 0.02 equal to almost 3.9. So almost 4. Okay, almost 4. Clear? Understand? So TR for 5% tolerance. Okay. TR for 5% tolerance. TR for 2% tolerance equal to 4 by zeta omega n. So 4 times tau. So this is for 2% tolerance. This is for 5% tolerance. Okay. If zeta increases, if damping ratio increases, the rise time, peak time, peak time increases, and MP decreases, maximum overshoot decreases. So if zeta increases, rise time, peak time, okay, increases, but maximum overshoot decreases. Maximum overshoot decreases. Okay. Next, what is dominant pole? Dominant pole. Dominant pole. If the system consists of more than one pole, okay, the system consists of more than one pole, the entire transient response, that is speed, okay, is determined or dominated by the near poles, and far away poles are ignored. So the when we consider the pole zero diagram, when we consider the pole zero diagram, so the near poles to the say j omega sigma real, this is S plane. Okay, this region, okay, this region near poles, these are all near poles region or dominant pole region. So this region from 2 times to 5 times to 10 times. Okay, this is some 5 times sigma to 10 times sigma. So this region is far away region. This region is far away. Far poles. So this is called the insignificant pole region. Insignificant poles region. Okay. So this is at least. This region is at least region. So this is dominant region. So what is dominant? If the system consists of more than one pole, the entire transient, okay, the entire transient response is determined or dominated by the near poles, and the far away poles are ignored. Okay, simply it is not a significant. Hence, the near poles are called dominant pole or significant pole, or poles. Okay, poles are very important. So the near poles called dominant pole. This is about dominant, right? So with this, we conclude our today's topic. Thank you very much.